All right, y'all. So today we are continuing our conversation about density. So we've looked at a little bit about how density and compactness are related. Remember that compactness, you are talking about how much stuff, so your mass, in a given amount of space, your volume. And so compactness and density are going to be related, right? If something is super compact, then it's going to be more dense versus if it's less compact and spread out, then it's going to be less dense. We've looked a little bit at the math and how that can work. And so those were great for when you had things that had perfect volumes, right? Either I was giving you the volume or we were using the simple length times width times height equation to get those volumes. But that doesn't always work. If you think about samples in the real world, they're not perfect little length times width times height or perfect round circles. And so today we're going to be looking at something called water displacement, which is going to help us figure out the volume of some irregular shaped objects. And then after we talk about it, you're going to have a chance to do it yourself. Okay, so density part 2. As a reminder, these were our guiding questions as we are looking at density. So how does a change in mass and or volume affect the density? Great, we've covered that one. How can density be used to determine if an object will float, sink, or like even suspend in the liquid, right? We've covered that one too. Think about that we had the ping pong ball that was floating on the water because it was less dense, and then we had the marble that sunk because it was more dense, right? So looking at the density of water, knowing that it's 1, if things are less dense, then they float. If they're more dense, then they sink. Next, it says, how can density be used to identify a substance? So we are going to take a look at that one today. Also, we've done a little bit of math with it, but I want to really dive in and explain how that's going to work. When we are doing our math, it's a good idea to keep in mind about our density triangle, right? So remember the way this thing works, okay, is that you cover up the one that you are wanting to solve for. So again, like if we wanted density, we would cover it up, and that would be mass over volume. Or if instead we wanted volume, then it would be mass over density for that equation. And then again, covering up mass, if that was what we were solving for, we would have density times volume. So again, this little density triangle is super helpful for reworking your algebra. Okay, so here's a problem that I would like for you to do. And so go ahead and work this out and then submit an answer. Awesome. Okay, so that should have been a good check back into the old material. So let's go ahead and move on to talking about water displacement and how that's going to work. All right, so what you can see here is that on the left, we have our first graduated cylinder. And that graduated cylinder, when we look at that initial volume, I said it looked like 13.5. You might have said maybe 13.2, 14, 13, right? There's definitely wiggle room when we're reading these things from a graduated cylinder. The way that you are going to read water in a graduated cylinder is something called a meniscus. A meniscus forms when water sort of makes that sort of curved look in the graduated cylinder, beaker, whatever it might be. Water's going to do that because it sort of sticks to the side. In the spring, we'll talk about cohesion and adhesion, which causes that meniscus to form. But yes, a meniscus, when you are looking at water in some sort of measuring device, you always want to take the reading at the bottom of the meniscus. So for example, if we were looking at a graduated cylinder like this, it's very fancy drawing, the water is going to sort of go like that. Not quite that drastic, but let's just go with it. So when you are looking at your markings on your graduated cylinder, the measurement you actually want to take is right here, okay? And again, that is your meniscus. You take your measurement at the bottom of the meniscus, which is a slight dip in the liquid in your measuring device, okay? And so first, you want to get a reading of how much water is in your measuring device. So that's step 1. Step 2, you're going to add your oddly shaped object into the water, okay? Step 3, you are going to record the new volume of your water. So if you notice in our picture here, we were initially at 13.5, okay? We added our oddly shaped mass, and then that water went up. I said it looked like roughly 22.4 at the bottom of that meniscus, okay? So then what you need to do is think about, okay, it was 13.5, and then that volume changed to 22.4. The water was displaced, there's that word, by the object. And so if that's the case, what do you think the volume of our object would be? Okay, so hopefully you figured that one out on your own. You're simply going to take that that final volume and subtract the initial volume, and that will give you that 8.9 milliliters is the volume of your object. Then the mass, right? Mass is easy. We just place that on a scale. Okay, so step 1 was to get the volume of our initial water. Step 2, add the object in. Step 3, record the volume of the water at that point. Step 4, subtract the initial volume from the final volume. Step 5, take your mass of your object. Done. Now you can use the density equation, mass over volume, and solve for the density of that object. All right, so let's take a look at this problem together. All right, so this 25, that was our initial volume. So I sometimes label it volume 1, volume initial, whatever's going to make sense for you, is 25 milliliters. All right, then step 2 was to add our object in, and then step 3 was to record that final volume. Okay, that was 33 milliliters. And so I can actually figure out the volume of my solid by taking the final volume minus that initial volume. And so 33 minus 25, that's going to give me 8, I think. 8 milliliters is the volume of my object. The mass was given to us right here in the question. Okay, again, in a real lab-like situation, you would record that using a scale. So now that I know my mass and my volume, I can simply go to my density equation, which is mass over volume. Remember that sweet little triangle, 2.34 grams divided by 8 milliliters. Okay, and so you're going to plug that into your calculator, 2.34 divided by 8. No worries about decimal places and things like that yet. We haven't talked about rounding. When we do, you'll know exactly how many decimals to put. All right, and so it's about 0.293 grams per milliliter. Again, those grams over those milliliters in our units here, grams over milliliters, okay? And so that's looking at that first water displacement problem. All right. So here you go. We've got a new problem to do. So go ahead and solve for the density of this sample of gold. All right, so remember that when we are doing this, right, we could read those volumes slightly different. So when I'm looking at that, I think my initial volume is like 15.1 milliliters. You may have said 15, you may have said 15.5, whatever, okay, somewhere in that range. It's based on how you're looking at it. Then I'm looking at it and I think that final volume looks like it's just under 20. So I'm going to say it's pretty close to 20. So how about 19.8 milliliters? And again, you may have said something slightly different. No worries. So then to get my volume of my object, I'm going to take the 19.8 and subtract the 15.1. And that is going to give me the volume of this odd object. Again, I didn't have a different way to get that volume. There's no beautiful equation for something that's oddly shaped like that. Okay, and so that's why this is super helpful to get those volumes. So the density is mass over volume. So 2.94 grams divided by 4.7 milliliters. We're going to plug that in. And we get 0.626. And again, if your answer wasn't exactly the same, that's most likely going to be based on, did you have different readings of the meniscus on the graduated cylinder, things like that. No big deal if that's the case. All right, so here's another one for you to do. So go ahead, again, take a second and solve for this one, please. All right, so now you guys are going to do an activity. So we're going to go ahead and pause the Ed puzzle for a minute, and then we'll come back in a little bit to take a look at that. All right, so layering. So we have been talking about layering a little bit, right, in terms of density, how it's going to work. So if things are of equal density, when you mix them together, they're going to mix beautifully and no problem. But most liquids and objects and things like that are going to have different densities based on the material that is making them, right? We know it's mass over volume, and the mass of different things is going to change. And so I really like this picture here because the layers of the liquid actually look like they're very similar volumes. Are they exact? I don't know. But you can see that the volume of each of those layers, other than the like objects, the bolt, the tomato, the bing bong ball, right? Those volumes look similar. So obviously their masses have to be different. And so again, it's those different densities that are going to cause layering to happen. And so if you think about even salad dressing, we spend a lot of time talking about salad dressing, but often you will see those separations of layers, right? The oils and things like that are involved. Or if you've ever gone to a restaurant, right, and they have those beautiful bread dishes and they pour the oil and the vinegar into your dish, and you see that separation of layers between those things. Density. Or if you've ever noticed that sort of like shiny rainbow-like sheen on top of puddles in the street after it rains, well, what's happening there is that the gasoline and the water have different densities, and so that gasoline, you see that kind of rainbow sheen. It's not mixing in perfectly with the water because of those different densities. And so we can get this cool layering effect happening. And so your next Flipgrid, you're actually looking at creating your own layers with objects at home. So make sure you take a look at Flipgrid and get that out there. The last thing I want to talk about is how we can use density as an identifier for substances out there. And so, you think about objects, even just things that I found in the chem lab. I'm like, oh man, I wonder what this is. Like, it's obviously some sort of metal. Like, what can I do with it? And so once I'm able to figure out the density, the nice thing is the internet, right? The internet has densities of numerous substances out there that we can take a look at. And so once you find the density of some sort of object, whatever it might be, you can look online and see if those densities are similar. Things are never going to be exact. There's rounding, there's maybe some extra dust on there, some extra dirt. So we're looking for closeness to a density. So here's a look at another problem. Looking at the mass for this thing, we are told that the mass is 5.00 grams and the volume is 0.476 milliliters. So right off the bat, we already know the mass and volume. That's great. Who knows how that volume was figured out? So we're going to take our 5.00 grams and put it over our 0.476 milliliters. We plug this into the calculator and we're going to get 10.50 grams per milliliter. So I calculated that mass and volume of my ring, I got the density, and I found that it was 10.50. I'm told in the question that the density of silver is 10.49. We're calling that close, okay? That's really close. Even if it had been 10.53, 10.4, those are very close numbers when you're thinking about the number scale. And so that right there, we are able to say, yep, my ring that I found or have is in fact pure silver. All right, so here is a problem for you to do. So I want you to submit your answer for the math, and then I want you to use Google, and if you can tell me what sample that metal might be. All right, y'all, so this wraps up our unit on density, and I hope you understand it a little bit better.